A stick is broken in 3 pieces by picking 2 points independently and uniformly along the stick. And then the stick is broken at 2 points, and we're asked what is the probability that the 3 pieces can be assembled into a triangle. We're also given a hint here that a triangle can be formed if the length of ABC, basically the segments, is between 0 and half. This basically fulfills the Pythagorean theorem, and hence we're getting the half from here. Okay, and the probability can be interpreted as geometrically as proportional to the area in a plane. We can avoid calculus altogether. So this is an interesting problem. We are let's translate what does it mean to have a stick. So any stick would be between length larger than 0 up to L, but we can normalize L such that it is always uniform. So let's draw a uniform length. So we say it now, it's 1 here. And we have to respect the condition that any length has to be no longer than half. So half is just here. And let's think about what happens when we draw these points. So let x be the first point and y be the second point. So x can land anywhere. Say x would land here. So this is little x. It's less than a half. And then say that y would land just here. Now this became a little tiny, but bear with me. So basically, then what is the length of A, B, and C? So the length of, let's write down what the length of A, B, and C is, the length of these segments. And so let's call A wherever x lands. And now, most importantly, we have to think about, we're assuming that x is less than y. So this is if x less than y. We will also assume the reverse, where x, if x is larger than y. Let's just think about what happens, because basically we can have the reverse points landing. So x can be larger, and then x would be here, y would be here. So these two situations will be symmetrical. So let's first think about what happens when. So let's just say A, which is the length of whatever x lands. So this would be A, and now B was whatever is the difference between y and x. So the difference here is minus x, and C would be whatever is left in the segment here. Well, C can be obviously anything that respects it being less than half, but we don't have to write out x as such. We just think about x being the remainder of minus A minus B, and A is just x, B is y minus x, and so we have basically C is 1 minus y. Okay, so now we have the segments. Here, and as given by the hint, let's try to translate this to the joint distribution of the uniform xy. So let's draw it out here. So say this is y, this is x, and this goes to 1, this goes to 1. And actually, just before I do this, let's write down what we are wanting to calculate. So we want to calculate whatever. I'm drawing a triangle here. It's saying this is an event. It's not referring to delta. I'm just saying what's the probability that a triangle will happen. Well, that's the same thing as A happening, so x happening, but that has to be less than a half. B happening, which is now y minus x being less than a half. And then C happening, which is 1 minus y less than a half. So we are looking for the event that respects this condition. Let's now think about what this means in this geometrical plane. All right, so half is an important number here, so we're putting it out like so. And thinking about segmenting the joint space of, so this is where we can, whoops. Okay, so these should be symmetrical rectangles here. Okay, so let's think about, well, now we are thinking about this particular situation where x is strictly less than y. What's that region? Well, the region of interest, so where does that happen? So here we have 0 to half, and y being from a half to 1. So it's somewhere in here. This is the region where we're thinking about respecting this condition. And the other condition is just symmetrically the opposite situation where y is less than x, so y is less than x, and this will happen in this region. So there's a triangle in here, and there should be a triangle in there. So what do I mean by triangle? I'm actually not referring to the same triangle, sorry, I'm just saying that this will result in a triangle when we look at these conditions. So let's look at these conditions and think about in which region we are. I think it's easier to look at these as well. So let's just simplify this actually, by the way. This looks like can be written as one event, which is that we know that y, so if we would simplify this, y is larger than a half, right? I just plus y to the other side here, and then negative, subtracting off a half, and then we're left with a half on this side. Here we are adding x, and then we see that y has to be a half plus x. And this is the lower limit of y, and this is the upper limit of y. So we can write it as one inequality instead of having two events like so. So y is larger than equal to 1/2 plus x and less than a half. Okay, so in this event, now we're in this region because we're conditioning if we're thinking about when x is less than y. This event here, it starts at a half, so it starts here, and then there's basically a line starting at a half again here, see, going up to x. So there will be a line crossing like so. So this is the triangle I was referring to. So what we are interested in integrating is this area here over this. And by symmetry, there will be an equivalent area over here when we're considering this part of the region. And now, thinking about what this means is that we have, so this base is a half and this height is also a half, right? So the area of this triangle is a half times a half divided by 2. So this region, well, we don't even have to actually do that calculation. We can think about the symmetry of the problem is that this area occurring is 1/4. Because we have 1, 2, 3, 4 regions. Half of that is 1/8. So this part of the region occurring is 1/8. But we have another triangle here, and that's also 1/8. So the answer is 1/4 when we add them together. And that is basically what the geometrical solution for this problem. Now, say that you wouldn't do this geometrically, but you at this point here thought, okay, I'm just going to do this by brute force. You know, maybe I didn't realize this geometrical trick here. Then, if we would continue at 1 here instead, how would we solve it in that case? So then we would have to do a double integral where we first we have two events and we are integrating over those events. So the inner integral is a half, going from a half. So now we're doing over the y space. I have to take the joint PDF. So we're doing dy first and then dx. And the outer integral goes from, so 0, x starts from 0, going up to a half. Okay. So, and I should say that we're now thinking about this as 2 of these rectangles here. Okay, so I'll be doing the same thing here. This is equivalent. Let's calculate this, and we know also that the PDF of 2 uniforms, it's IID first of all, and of each of these PDFs we have a value of 1, which makes us quite comfortable. All right, so we have then 1 dy dx. We're integrating over half plus x, and this should be a half, by the way, like so. So the first, evaluating this inner integral, we have y half, a half plus x. And the outer integral like so. And this inner part evaluates to, so we have a half plus x, and then will be minus a half. So what we're left with is just a x here. So let's write that out, dx. Now we're evaluating that integral. We end up with x2, a half over 0 to a half. And that is basically half 1/4. Right, and we have these two integrals twice, so it will be another 1/8 here, because the problem is exactly symmetrical, and so this will be 1/4. Moving on to part B here, and now we are asked about the parameter of a table, and we're going to position 3 legs uniformly, and we are asked what's the probability that the table will stand. Well, that's an interesting problem. We're not giving much information about what does it mean that a table will stand. So we have to reason a little bit about that and assume that the table respects our assumptions about it. So let's draw a table, a circular table, like so. Let me just increase the size of it, and we're going to draw, well, let's just take half of it like so, and think about what does it mean for a table, what does this problem mean geometrically. So the circumference of the circle, again, as in the stick problem, we could put it as L, as in length, or we just normalize and say this length respects a uniform distribution, like so. Okay. Now let's think about what would it mean if we would position 3 legs. I mean, a perfect positioning would be something like, perhaps we'll have a leg here, and a leg here, and a leg here. Okay. If we would put a leg here, obviously, if we wouldn't put a leg there, say, the table wouldn't stand, right? Very clearly so. But if it would be something like this, it looks reasonable that the table will stand. And now we can see that this sort of resembles the first problem of having a triangle. And so a triangle is probably what we are looking for. Okay, so let's then say that we have, let's say that we would divide, as I did now, would divide the circle into 2, and then reason about the properties of it being respecting this sort of triangular motion. Could it be the case that this probability is even exactly 1/4, as we have calculated here previously? Let's think about it. Okay, so we can do this in different ways. Let's do the following. Let's say that we have a couple of different situations. So we can say, duplicating this just to have this as a scratch point. Say that the first point would be positioned here, A1. Okay, and so we're fixing it, say, and then we have this half circle. Now we have this half circle, basically a semicircle. We're asking, and we can ask, what's the probability that A2, so the second leg, would fall into this region? Okay. Well, now by looking at the area, we're saying basically that this is half here, right? It's 1/2, and the second one also falling into this region is also 1/2. So we have the probability that, say, I'll just call this the probability that we have a semicircle. This event now, A1, is a semicircle, and saying A1 is a semicircle and the 2 other legs will fall into the semicircle. Basically, we have a failure here. So this would be 1/2 times 1/2. So that's 1/4. Okay. And by symmetry, this A1 could be anything, right? So it could be any of the three legs. So we have another area where, another event where A3 happens, and that's also 1/4, right? And the same with, sorry, A2, A3. This would be also A4, 1/4. And so what does it mean? So basically it means that we're trying to find out the complement. And so it could only be that these legs will fall into this area only once for all of these events. So basically we have that the probability of A1, A2, A3 not happening is, they're disjunct, is, so it's called this AJ complement, so this is not happening, is 1 minus 3/4. So I'm just summing these probabilities. And what remains is 1/4, and that event is exactly the event when we have a triangle. And that is indeed then the same answer as we thought in terms of A1.